Hello guys, you're welcome back. In this lesson we are going to be studying how to solve Bernoulli's equation. A Bernoulli's equation is a non-linear differential equation, usually of the form y prime plus some function p of x, y equal to some function r of x, y raised to power a. Notice in this case the power a here is not equal to 0 and the power a there is not equal to 1. If the power a has been equal to 0 or 1, this differential equation would have been linear and we'll be able to solve it using the method for solving the linear differential equation. But this here makes this non-linear. Another reason for which a differential equation can be non-linear is when you have a product of the function y and one of its derivative, maybe its first derivative of its second derivative. So, but in this case we don't have that, but the power a here is other than 0 or 1. In that case, this differential equation is said to be non-linear. So this particular one is the general form of a Bernoulli's equation. So how do you solve this kind of differential equation? What you do is we need to rewrite it in linear form. To rewrite this differential equation in linear form, what you will have to do is we are going to set a function u of x and let it equal to y raised to power some function y of x raised to power 1 minus a. Actually, in this lesson, what we are going to be doing is I will walk you through the process of obtaining a formula for rewriting the form of a Bernoulli equation in linear form. Then you can then go on and solve it using the linear method. So, and that is what I am going to walk you through. And towards the end of this lesson, we are going to solve a problem to test and see if the method we just learned is actually practical. So after you set this function u of x equal to y of x raised to power 1 minus a, take the derivative of u. What's the derivative of u with respect to s? The derivative of y with respect to s, y raised to power 1 minus a, with respect to s is going to be 1 minus a, y raised to power 1 minus a and minus 1, and multiplied by y, the y ds, or y prime. And that's because you are taking derivative of y with respect to s. So since it is not x, we don't have x here. So in that case, you multiply it by the y ds, right? So next, this is going to be derivative of u is 1 minus a, y raised to power negative a, and multiplied by y prime. From here, if we call this 1, from 1 here, we can rewrite this as y prime equals r, let me just put down ry raised to power a n minus p y. Let me just put down p there. We know p is a function of x. We can rewrite this as this. So let us go on and put this y prime here. Let's replace it here such that we have u prime equals 1 minus a, y raised to power negative a, and multiplied by ry raised to power a and minus p y. If we open the bracket here, we have 1 minus a, and multiplying y raised to power minus a by ry raised to power a, we are going to have to add up minus a and plus a, which should be 1, which should be 0, and then we have y raised to power 0, which is equal to 1. So this is reduced into r, and y raised to power minus a multiplied by py, multiplying y raised to power minus a by y raised to power 1 would make that py raised to power 1 minus a. So I hope you agree with that. So we have u prime on this side. So let me replace y raised to power 1 minus a with u, because we've said it earlier on that y raised to power 1 minus a is u. So I'm putting u here. So we have u prime is equal to 1 minus a and r minus p u. And from here, if I distribute what we have inside the bracket here to the component in here, we have 1 minus a multiplied by r and minus 1 minus a multiplied by pu. So from here, if I bring this on the other side, this negative 1 minus a pu, I'm going to be having this formula u prime plus 1 minus a pu equals 1 minus a r. You will notice at this point that this new differential equation we obtain is of the form is similar to y prime plus py equals r, which is the linear form we are very well aware of before. So you will notice now that we have rewritten the Bernoulli equation now in linear form. So, and to solve this linear form, remember the function u here is, okay, let me call it y. Let me call it y for now. Y is going to be equal to 1 divided by e raised to power h into the integral of p into the integral of e raised to power h and r ds plus the constant of integration. Where this e raised to power h is what you call the integrating factor for this non-exact differential equation, because this differential equation is going to be non-exact, and there is the integrating factor. If you need lesson on how to obtain the integrating factor of the differential equation, I'm going to put a link to that. I also put a link on how to obtain the solution for linear differential equation down in the description. So where the h here is equal to the integral of p dx, if you recall. So now we can now go on and solve this using the exact method. And don't forget, earlier on we have set the function u is equal to y raised to power 1 minus a. Well, let us test this out and see if this actually works in solving real problem. So what if we have this problem to solve? Y prime plus 2s squared y equals y raised to power 2. So we agree this differential equation is non-linear. So how do we solve this? So let's walk through this process. So we wanted to rewrite this in linear form, so we are going to make use of this formula. So this differential equation then become u prime. So let me write it side by side there. So in this case, you will notice that the p we have here is 2x squared, and the r is 1, and the power a is 2, such that we're going to be having u prime and plus 1 minus 2 and multiplied by p, which is 2s squared. Then I'll put down u is equal to 1 minus a, 1 minus 2, and multiplied by r, which is 1. This would be u prime minus 2s squared, and u equals, this is negative 1. So you will agree that this is similar to the form y prime plus p py equals r. So in this case, it's obvious we have p is equal to negative 2s squared, r is equal to negative 1. So the solution to this differential equation is going to be u, which should be equal to 1 all over e raised to power h into the integral of e raised to power h r dx and plus c. So we need to find h first. So the h we have there is going to be equal to the integral of p dx, and where p here is negative 2s squared and dx. So if we evaluate this integral, this is going to be equal to negative 2s raised to power 2 divided by 2. These two cancel out these two, and you have negative s squared. So the integrating factor is going to be e raised to power negative s squared. So let us go on and put that in there. So we have u is equal to 1 all over x raised to power negative 1 all over e raised to power negative s raised to power 2, and into integral of e raised to power h, integral of e raised to power negative s raised to power 2 multiplied by r, in this case, which is negative 1, multiplied by negative 1, the x, and plus c. So if I have to, we have this integral to evaluate in here. So this will be equal to 1 all over. So this will be equal to e raised to power s raised to power 2. When we evaluate this, and into the integral here, let me bring out this negative. The integral for e raised to power negative s raised to power 2 is going to be e raised to power negative s raised to power 2. And we are going to divide it by the derivative of s raised to power 2. Negative s raised to power 2, it should be negative 2x. I have bring this out here, and this is it. So n plus c. So u is equal to e raised to power s raised to power 2 into this negative cancel out this negative here. So we have e raised to the power negative s raised to the power 2 and divided by 2x. Oh, I didn't put plus c there. And plus c. So when I distribute this into the content inside the bracket, so this we cancel out this, and we have 1 all over 2x and plus c e raised to the power x raised to the power 2. So this is the solution for u. Well, we are looking for the solution for the original differential equation, which is y, which has y function, right? So remember we said u is equal to y raised to the power 1 minus a, where a in this case is equal to 2. So this will be equal to y raised to the power 1 minus 2, which is y raised to the power 1 minus y raised to the power minus 1, and that is equal to 1 over y. So if u is equal to 1 over y, then y is equal to 1 over u. So the solution, y here is going to be 1 all over everything here, 1 over 2x plus c e to the x raised to the power 2. And this right here is the general solution for that of the differential equation. And that's how to solve the Bernoulli's equation. Well, see you in the next one.